So what you learn in wave optics is first how they discovered the wave nature of light. What are some of the observations and experiments that led to the discovery that light is a wave? Okay, because earlier in Newton's time, it was thought that light is a collection of particles. Okay, and those particles of light were called corpuscles. Okay, and that theory that light is a collection of corpuscles traveling as a uh, group or a bunch, okay, is called corpuscular theory of light. Fine, and it was thought, okay, that light is a collection of particles, and Newton and some other scientists, they even gave equations which proved that, or which explained the behavior of light. Okay, but one thing they thought in those days that is that when light undergoes refraction, okay, we know light bends, okay, when it travels from one medium to another medium. They knew it in those days also, that light bends from when it travels from one medium to another medium. So one thing they thought was that when light enters from one medium into another medium and bends towards the normal, okay, let us draw a diagram of that. Suppose this is the interface separating two media, okay, and a light ray incident like this bends towards the normal. Now, can one of you quickly tell me when light bends towards the normal, when it travels from rarer to denser medium or denser to rarer medium?
Rarer to denser.
Rarer to denser, correct. So this must be the rarer medium and this must be the denser medium. We know that if it travels from rarer to denser, it bends towards the normal. And in a denser medium, the refractive index is high. Does that mean, okay, from what you learned from ray optics, does that mean light travels faster in denser medium or slower in denser medium? From the definition of refractive index, you tell. If refractive index is high, does it mean light travels faster in that medium or slower?
Slower.
Slower, correct. Because refractive index of a medium is nothing but speed of light in vacuum divided by the speed of light in that medium. If speed of light in medium is slower, refractive index will be higher. Okay, we know this now. But in those days, okay, when corpuscular theory was popular, uh, it was proved using some equations. They proved that if light bends towards the normal, then it must be traveling faster in the second medium. Okay, that is what they used to think. So according to corpuscular theory, light travels faster in a denser medium. Okay, so those days they didn't, probably in those days, this formula for refractive index also would not have existed, obviously. Okay, so in this chapter, what we are going to learn is some observations and experiments which proved that light has wave nature. And using that theory of wave nature of light, we can even prove the law of reflection and the law of refraction, that is Snell's law. Okay, and it can be proved, Snell's law can be proved if, I mean, whatever we are observing in refraction, okay, the bending of light, it can be proved theoretically if light travels slower in a denser medium. Okay, that is what we are going to learn in this chapter. So we'll be talking about the wave nature of light, how it was discovered, then some experiments which proved the wave nature of light, which is Young's double slit experiment and single slit diffraction, and some experiments related to polarization of light. Polarization of light proves that light is a transverse wave, not a longitudinal wave. There are two types of waves, transverse, longitudinal. So polarization experiments proved that light is a transverse wave. So all these are what we are going to discuss. right? First, assume there is an opaque wall. Opaque means a wall which does not allow light to pass through it with a small gap in it. You can think of it as a boundary with a small gap in it. And assume there is another wall here at a certain distance from it, parallel to it, like this. Fine. Now, if a parallel beam of light is incident on this wall, what do you expect to see on the other wall? Like suppose this gap here in the first wall has a width d, or you can assume it's in the form of a circle of diameter d. Let's say a parallel beam of light is incident like this. Assume the gap in this wall is in the form of a circle of diameter d. What do you expect to see on the other wall? Anyone? I got one answer as a bright fringe or a bright spot in the middle. Okay. Fine. Prajin is telling the actual thing that you will see. A bright spot in the middle and then alternating bright and dark bands. Why would you expect that? Okay. Normally, we know that light travels in a straight line. If light only travels in a straight line, then what we expect would be something like this. The light should continue traveling like this and strike the other wall in this region, and you should see a bright spot in this region on the other wall. Okay, if light only travels in a straight line, this is what we would expect. Okay, but what actually happens, okay, is that you will see most of the light, or you will see a very high brightness in that circular spot, but you will also find some light away from that spot. Okay, light actually bends when it passes close to this boundary. This is what you will actually observe. So corpuscular theory could not explain these observations. Why light bends when it goes close to a boundary like this. Okay, that could not be explained by corpuscular theory. So they had to come up with some new ideas or a new picture of light to explain these observations. Okay. So that is when it was actually thought. I mean, these experiments are what made them think, these observations are what made them think that maybe light has wave nature. But why did wave nature come into the picture? Okay. Now you consider something like this. Suppose there is let's say there is a house, just a moment. Okay, you consider a house like this. You can see there is, okay, let's say there's an entertainment unit somewhere here. Where? Okay, somewhere here. Let's say there is a TV set somewhere here. Suppose it is turned on, produces sound. Sound is a wave. Okay, it's a mechanical wave, right? Now, the TV set, if it is producing sound, those sound waves, they can travel to every point in this room. That's fine. Okay, so that sound can be heard everywhere in this room. But if the volume is high enough, can the sound be heard in the other rooms also or not? Yes or no? What do you observe? Not just a TV, even if a person speaks, can you, if the person speaks loud enough, can you hear the sound from other rooms also or not?
Yes, sir.
It can be. Okay. Now, one possible explanation of that is that sound gets reflected. Okay, when it hits the walls of a room or something, it gets reflected, and maybe some of the reflected rays travel like this. Okay, the waves get reflected and travel like this. Maybe multiple reflections, they reach the person in the other room or whatever. That is one way it can be explained. Okay, but there are other ways also to explain it, not just in case of sound. This happens with waves on surface of water also. Fine. You assume the screen is a water surface. Okay. So what happens when you drop a stone on a water surface? It creates waves. Okay, it creates ripples, right? So you see circular waves. Suppose a stone is dropped somewhere here, then around the stone you see disturbances expanding, circular disturbances like this. Okay, but if there is a boundary somewhere here, let's say there is a rigid wall somewhere here with a small gap in it, and there's water on this side of the wall, there's water on that side of the wall as well. Okay. So what you see near this gap is that the water waves, okay, the waves on the surface of water, they spread out like this, as if the disturbance was created here and not here and not at the original point. Okay, that small gap in the wall behaves like a source of waves, or that itself behaves like the point where the stone has been dropped. Okay, so basically what is happening, these water waves which are traveling like this don't just travel in straight lines, they appear to bend at this boundary. Okay, and the same happens with sound also, and these things they knew in those days. Okay, the behavior of mechanical waves, see, water waves on the surface of water and sound waves, these are mechanical waves. Particles in the medium oscillate back and forth, okay, or up and down, producing these waves. Fine. So in mechanical waves they knew this happens. Basically why this happens is, see, when you drop a stone on the surface of water, that stone disturbs the particles which it touches. Fine. And because of elasticity of the medium, okay, what do you mean by elasticity? Molecules of the medium will be connected to each other. Fine. So there will be some bonding between them. So if you disturb one set of molecules, what happens is they will disturb the layer next to them. Okay, second layer. That second layer of molecules, once it is disturbed, disturbs the third layer of molecules. That third layer disturbs the fourth layer and so on. Okay, so if one molecule is disturbed, it disturbs all the molecules around it. Basically, that's the idea. Fine. So you observe this gap that is there in the wall. There are a few water particles in that gap also. Okay, water particles or water molecules in that gap. So once that particle gets disturbed, what happens is it disturbs all the particles around it. You can't expect a particle to disturb another particle only in one direction. Okay, because that particle is connected to other particles all around it, not just the particle in one particular direction. Fine. So if that one water particle goes down due to some disturbance, then it will pull all the particles around it down. So not just a particle in one particular direction, it pulls particles in all directions down. That is why the wave spreads like this, as if this particle itself is the source of waves. The same happens with sound also. Okay, sound is a longitudinal wave. One layer of molecules get disturbed, one layer of air molecules or whatever is the medium through which sound is propagating. If one layer gets disturbed, that layer disturbs the next layer and so on. So when sound reaches a boundary like this, the layer of molecules which are near the boundary, they will start behaving as the source of waves. Okay, and disturb layers around them. So suppose this was a sound source, like a speaker or something. You don't just hear sound in this region. You hear sound even here because some waves propagate this way also. You hear sound even at this point because some waves propagate this way. So this is what happens with mechanical waves. Effectively, every particle of the medium behaves as a new source of waves. And that makes sense. That is what is a mechanical wave. No, if one particle is disturbed, it has to disturb the particles around it. Okay. Now the same behavior was observed in light here. Instead of traveling straight as expected, okay, as was thought in those days, light travels in straight lines. Instead of traveling straight, it is actually bending, okay, when it passes close to a boundary. So they thought that maybe light has wave nature because water waves and sound waves show this behavior of bending when they pass close to a boundary. Okay. So let's discuss this idea first. This idea is called Huygens wave theory. Okay. Basically, Huygens was the one who proposed that every particle in a medium behaves as a wave. Okay, that is how you can explain this bending of waves, bending of energy, okay, that passes through a particular medium. So basically, in Huygens wave theory, first thing he talked about is something called a wave front. Actually, to understand the theory, you don't need to know what is a wave front, but he defined something called a wave front, and based on that, he explained. Okay. Now, consider this picture. Just a moment. Suppose a stone is dropped on the surface of water. You see a disturbance like this created on the surface. So the exact point where the stone is dropped, this point is the primary source of the disturbance. Okay. So the point where the stone is dropped, at that point, the water molecules get disturbed. Okay. So like stone is dropped from above, the water molecules get pushed in the downward direction. Now those water molecules are connected to the other molecules around them. So the first set of molecules, when it goes down, it pulls the next set down along with it. There will be some lag between that. All particles won't go down together. If one particle goes down with some lag, with some gap, okay, depending on the tightness or the elasticity of the medium, with some gap, the next layer will start going down. Okay, and then with some time gap, the third layer will start going down and so on. So the actual point where the stone has been dropped is the primary source of these waves or these disturbances. Now, as you can see, when these waves propagate outward, they propagate in the form of troughs and crests. There are some ups and downs in this medium, as you can observe on the surface of water, and so on. Okay, and you can see these crests and troughs in all directions, not just in one particular direction. There's a trough here, trough, crest, and so on. These are propagating in all directions. And you can see that the disturbance propagates in the form of circles on the surface of water. Now you consider a set of particles, let's say this set that I'm marking in green. From what you observe in the diagram, what is common to all these particles? That set of particles that I have marked in green, what is common to all those particles?
It's being disturbed by the primary source, sir.
Okay, fine. You are saying that's the layer immediately next to the primary source. Okay, there is a lot of gap between them actually. Fine. See, every particle in the on the surface of water is getting disturbed. What else? What else is common to these to this set of particles? Okay, I got one answer in chat as their phase of oscillation. Correct. All these particles that I have marked, these are all part of a single crest, as you can see. Okay, all those molecules are raised up compared to their uh, what do you call mean level or the average level at which they would be present. You can consider another set of molecules also. Maybe uh, okay, let's consider a trough now. Fine, you take a set of particles like this. These particles are also on a circle, but all these particles are in a trough. They are in a depression, as you can see. Okay. So they are all in the same phase of oscillation. They have all gone down compared to their mean positions. Right? So you see crests and troughs forming like this alternately. So all particles which are on a particular crest, okay, like the green particles that we have highlighted, they all reach their topmost position at the same time. Okay, they all reach their positive extreme at the same time, and after some time, as these ripples expand, the same set of green molecules, okay, will go down also. They will form a trough. Again, they will rise up. They'll form a crest. They'll form a trough. It depends on how many times the primary source is disturbing the water surface. Okay, so if the primary source keeps oscillating, the particles around it also will keep oscillating up and down. So basically, this set of molecules which we have connected in green and the set of molecules which we have connected in pink, these are called wave fronts. This is one wave front. The set of molecules we have highlighted in green is another wave front. So basically, what is common to all the particles that are highlighted in green? They are undergoing the same phase of oscillation. They all reach their positive extreme at the same time. They all go to their mean position at the same time. They all go to their negative extreme also at the same time. They oscillate in phase. Okay. And the continuous distribution of particles which oscillate in the same phase is what you call as a wave front. Okay. Remember this definition. This is very important. The locus of points. Okay. Locus means continuous distribution. Okay. Of points which oscillate in the same phase when waves pass through them is called a wavefront. Fine. So as a wave propagates through a medium, okay, as a wave passes through a medium, you can draw wavefronts like this. On the surface of water, it's literally visible. You can see the wavefronts. Can one of you tell me the shape of these wavefronts formed on a calm surface of water when it is disturbed? What shape are they? What is the basic shape of these wavefronts?
Circle, sir.
Circles. Okay. So we call these the wavefronts forming on the surface of water are circular wave fronts. Okay. Now, basically, when do you get circular wave fronts? The surface of water is a two-dimensional surface, right? Two-dimensional distribution of molecules. In a two-dimensional distribution, if there is a point source, okay, one point of disturbance, then you get circular wavefronts like this. So on a two-dimensional distribution, in a two-dimensional distribution of molecules, you can get circular wavefronts if there is a point source. Now you all tell me, suppose there is a small speaker. Okay, so basically a source of sound. Let's say there is a small source of sound in space, three-dimensional space. I mean, when I say space, I don't mean space where there is no air and all. I'm just saying there is a sound source in a medium which is distributed all around it. Okay, let's say there is air all around this source of sound. You switch it on. In which direction does sound propagate from a point source? Like if there is a small speaker in your room and you switch it on, okay, these days you have speakers shaped like a ball also, like a sphere. Okay. You switch it on, you hear sound in all directions, no? So sound is propagating from the speaker or from the source in all directions. And see, on the screen, we will only be able to show these arrows in the plane of the screen. But if you visualize these waves, the sound propagates in all directions in 3 dimensions. Fine. So suppose this is a point source of sound, means a very small source of sound. What it does is it disturbs the layer of molecules next to it first. Okay. So assume this sound source is in the form of a sphere. A point is basically a sphere of radius tending to 0. Okay. So assume this one disturbs the layer of molecules next to it. So what will happen? That layer will disturb the layer next to it. So basically this disturbance will be passed forward. Fine. So just a moment, let me take a collection of points like this. Okay. Assume this is one set of particles which are disturbed by this sound source. So this set will disturb the next set. See, sound propagates in the form of longitudinal waves, so compressions and rarefactions. So let's say there is a compression at these particles now. So next moment, what will happen? These particles will disturb the layer next to them. So the disturbance expands like this. And it continues to expand like this. Fine. As long as the medium is present, it continues to expand. And if the sound source continues to produce disturbances one after another, you can assume another layer disturbed by the sound source. So the first disturbance is propagating, it is expanding. Now the sound source has created another disturbance. So what happens? The first disturbance keeps expanding, and the new disturbance that has been created, that will also expand. Like this. So as the sound source keeps creating disturbances, the disturbances will keep expanding like this. And if you visualize this in 3 dimensions, okay, they'll be expanding like spheres. Are you all able to visualize that? Okay, these disturbances, as they propagate, they'll be propagating in the form of spheres. So basically, suppose this is a compression. Okay, in between, let's say there's a rarefaction and this is another compression. And in between, there is a rarefaction and another compression. So these compressions and rarefactions will keep expanding in the form of spheres. Now, you connect all the particles which are disturbed in the same manner. Okay? For example, you connect all these particles which form the first compression, the smallest compression that you see here. They will become one wavefront because they are all undergoing the same phase of disturbance. They are all at the they are all seeing a compression pass through them. Okay, so that becomes one wavefront. Next, you can connect all these particles which are also part of the compression. Okay, they all have a compression going through them at the same time. So this becomes another wavefront. And then you can, okay, you can even connect these particles which have a rarefaction passing through them at the same time. So that becomes another wavefront. They are all undergoing the same phase of disturbance or the same phase of oscillation. So that becomes another wavefront. Now on screen, these wavefronts look like circles. But tell me, what is their actual shape? Anyone? In 3 dimension, as these disturbances expand, what is their actual shape? Isha, what will the shape be? Rishi, what do you think the shape will be in 3 dimensions? You just have to imagine layers of molecules, okay, being disturbed one after another. So in what shape does the disturbance propagate is my question. Pradyun, your answer is correct. Nitya? See, on the surface of water is a 2-dimensional surface. Okay. If you consider a point source, a single point of disturbance, okay, it disturbs the layer of molecules next to it, that layer disturbs the layer next to it, and so on. On a 2-dimensional surface, they spread in the form of circles. Okay. In 3 dimensions, how does it spread is what I'm asking. In 3 dimensions, you will see them spreading in the form of spheres. Okay, Isha, correct. You also have given the answer as a sphere. Okay, particles on all sides or in all directions will be getting disturbed. Okay, so in 3 dimensions, they spread out in the form of spheres. So these wavefronts, these are also collections of particles which are undergoing the same phase of disturbance. No, the pink circle that I have drawn here, the purple circle that I have drawn here. On screen, they look like circles, but these are actually spheres. Fine. So this sphere becomes one wavefront. This purple sphere becomes another wavefront, and so on. So basically, we considered waves from a point source, okay, in 3 dimensions, in a 3-dimensional medium. Then the kind of wavefronts that it produces are spherical wavefronts. So remember this point, in a 3-dimensional medium, a point source produces spherical wavefronts. In a 2-dimensional medium, a point source produces circular wavefronts. Okay. Suppose there is a long linear source of waves. You imagine something like this. Okay. Assume every point on this line is a source of waves, or this entire line is creating the disturbance. Okay. Okay, Pradyun, what you have said is correct. But others, try to imagine, see, this entire line is a disturbance. Fine. and there are particles all around it. Okay, or let's consider a two-dimensional medium itself. Pradyun, your answer is correct for a three-dimensional medium. You also visualize this. Suppose there is a two-dimensional medium. Okay, like water surface itself. Assume there's a calm water surface and you drop a stick onto it. Okay, and it's a very long stick. Fine, or maybe you drop a long wire onto the surface of water. So there are water particles on the right side of this wire. There are water particles on the left side of this wire. So this wire, when it is dropped on the surface of water, it disturbs all the water particles which are on that line. Okay, now those particles, you visualize them disturbing the surrounding particles, and you tell me how the disturbance propagates, in what shape it propagates. Try to predict. I want answers from all of you. You can type in chat if you want, or unmute and tell. But if there is a linear disturbance like this, okay, if we disturb an entire line of particles on the surface of water, how do you see the disturbance propagating is my question. Okay, think and answer. I'll give you all 2 minutes. Okay, let's assume they are circular with the center at the center of the linear source. What you are indirectly saying is, see, as the circle expands, let's assume this is a crest that is expanding. So you are saying there is a crest at this point, there's a crest at this point, and there's a crest at this point. How is that happening? The entire line of molecules is disturbed at the same time, no? Fine. So you first imagine this source, the thick blue line that I have drawn is the source of disturbance, okay? You imagine this thick blue line oscillating up and down. It's not a single oscillation. You assume it continues to oscillate up and down. Fine. When this thick blue line rises up, it creates a crest. When this thick blue line goes down, it creates a trough. On all those molecules, it creates. Okay. So all the molecules along this line are getting disturbed. Then they will disturb the layer of molecules next to them. So effectively what happens is every point on this line behaves as a source. Obviously, every particle of the medium that is getting disturbed disturbs the particles all around it. Okay, so every point on this line behaves as a source now. Okay, now this point disturbs the layer next to it. This point disturbs the layer next to it. This point disturbs the layer next to it. Okay, this is true. Every particle disturbs every other particle around it. Okay, you can't say no to that. That will automatically happen because of the elasticity of the medium, because the particles are connected. Okay, and as I said, that connection is not only in one dimension, no, that connection is there with every particle surrounding it. Okay, so if one particle is going down, it will take all the particles surrounding it down. So disturbances will be created like this at every point, and there are infinite points on this line. Okay, but effectively what you will see is something like this. Just a moment. Suppose you first created a trough. Let's say this thick blue line of molecules that is there have gone down. Then what they will do is they will take the layer of molecules next to them down. So you will see these molecules forming the trough next. Okay, and same on the left side as well. And that trough will keep expanding. Okay, so this disturbance will keep traveling forward. On both sides, it will keep traveling forward like this. And after some more time, you may see the trough travel to this position. Even on the other side, you will see it traveling forward. Okay, so in a two-dimensional medium, if this is actually a water surface, what you will see are lines. Okay, not circles. Rishi, is this clear?
Yes.
lines or linear wavefront, you can say, in a two-dimensional medium. If the same happens in a three-dimensional medium, suppose there is medium all around this long linear wire of disturbance, okay, then what you will see are cylindrical wavefronts like this. The disturbance has to spread in all directions away from the wire. Okay, so spreading in all directions away from the wire, you will have cylinders like this. So a long linear source of waves produces cylindrical wavefronts. Okay, in 2D medium, it is lines or linear wavefronts. If it is a three-dimensional medium, you get cylindrical wavefronts. Fine. So basically, this is how mechanical waves propagate. Okay, and what is Huygens wave principle? Wave principle or wave theory, the idea that he used to explain this behavior of waves is that every point on a wavefront behaves as a source of waves. Every point on a wavefront behaves as a source of waves. In fact, you don't have to use this term every point on a wavefront particularly. In fact, every point in a medium through which a wave is propagating behaves as a source of waves. Okay, once a particular particle is disturbed, it disturbs the particles around it. Obviously, that particle will be part of a wavefront. Okay, so if waves are passing through a medium, every particle of the medium will be part of a wavefront. Okay, some or the other wavefront. For example, all these particles are part of one wavefront. Okay, then all these particles are part of another wavefront. In fact, there will be wavefronts in between them also. We can't draw all of them. Okay, so you don't have to specifically say that every point of a wavefront behaves as a source of wave. Every point of a medium through which waves are propagating behaves as a source of waves. These sources are called secondary sources. Okay, like in that stone dropped on a water example, the first point, which is first point of water or first particle of water, which is actually disturbed by the stone, is the primary source of disturbance. Okay, but that particle disturbs the particles next to it, and those particles disturb the particles next to them. All these are called the secondary sources. So there will be infinite number of secondary sources. Right? This is what is Huygens wave theory and wave principle. Okay. Basically, this is like Huygens explained how waves propagate using this idea. Okay, once a particle is disturbed, it disturbs all the particles around it. That's the idea. Okay, now what does Huygens wave theory help us predict about waves or help us tell about waves? It can tell you how waves are going to travel. Okay, how the disturbance travels, you can predict. Now you consider what do you call waves on the surface of water itself. So basically, we are considering a two-dimensional medium. Let's say the screen itself is the surface of water. Fine. If you create a disturbance somewhere, maybe at this point, what will happen? It will disturb the set of molecules next to it, and the entire set of molecules next to it will get disturbed in the same manner at the same time. Okay, so they will be having the same phase of disturbance. You can consider it like this. The immediate next layer of molecules will be, that entire layer will be disturbed in the same manner. Okay, you can think of this as the first layer of molecules next to the primary source. So let's assume this first layer has been disturbed. Now what happens? Every point on this first layer behaves as a source of waves. Okay, let me take this slightly bigger, just a moment. Okay, let's say this is the first layer of molecules after the primary source. I am considering significant gap between the layers. Let it be. Now, every point of this layer which has just been disturbed behaves as a source of waves. And they have medium all around them, right? So these sources will disturb all the particles surrounding them. So basically what happens is something like this. Secondary disturbances start getting produced. So this particle creates a disturbance like this. This particle creates a disturbance like this. And they do this at the same time because the first set got disturbed at the same time. Now all particles of the first set got disturbed at the same time. So they will all start creating new disturbances at the same time. Like this. You have to imagine infinite circles on this circle. And as time passes, you know that the ripples expand. So let's say at one time t1, the ripple was in the shape of that circle. Then after some more time, let's say delta t, after a short amount of time delta t, that circle would expand. No, you must have seen waves expanding on the surface of water. The circles keep expanding. How they expand is in this manner. In a short time delta t, let's say each of these secondary waves expand by a certain distance. Okay, secondary disturbances expand by a certain distance. Then what happens? The primary disturbance that was there, not primary, the first disturbance that was created effectively expands to this size now. Okay, this is what we can just a moment. This is what we can predict using Huygens principle. Like after a certain amount of time, what happens to a particular wavefront? How does it expand or what new shape does it take can be predicted using Huygens wave principle. So how exactly do you do that? See, in this example, we first took one wavefront, which is in the form of a circle like this. Okay. Then what we did is we considered every point on that wavefront as a source of waves. So we imagined them emitting waves in all directions or creating disturbance in all directions. Now that disturbance also won't be static. No, it will propagate. Okay. So in a small time delta t, the disturbances created by each of these secondary sources would expand a little bit. So you draw circles around those points and then you draw a common tangential surface. Okay, this is a common tangential surface drawn to these secondary wavelets. Okay, these small circles that we have drawn here, they are called wavelets, these ones. When you draw a common tangential surface to all those wavelets after some time, okay, you can tell what is the shape of the initial wavefront after some time. So basically what I'm saying is this first circle that is there, the thick circle that I have drawn, it expands to this form in a time delta t or after a time delta t. So using Huygens wave principle and using the idea that every point on a wavefront behaves as a source of waves, you can tell what happens to that wavefront after some time. Okay, how that wavefront will look after some time, you can find out. So, and in fact, this is what we observe now on the surface of water. We see those circles expanding. Each circle is a wavefront, and the wavefront is expanding. This is how it expands. Okay. Now, some of you may ask, like, sir, the wavelets or the secondary sources that are there, those points on the circle that I have considered, they are creating waves like this also. So what about this wavefront, which should actually be traveling in the backward direction? It's called the back wave. Okay, there are forward waves and there are backward waves also. Okay, Huygens principle does not explain what happens to this. That is a drawback of Huygens principle. Okay, if every point behaves as a source, those sources will be sending some disturbance in the backward direction also, opposite direction. What happens to that disturbance? There is no explanation to that. Okay, so you can remember it as a drawback of Huygens theory. So the back wave is not explained by it. Fine. Now try this, all of you. Basically what we will do is, we will consider some wavefronts. You imagine every point on that wavefront as a new source of waves, and you draw the shape of the wavefront after some time. Okay, so suppose there is a wavefront like this. Just a moment. Consider an S-shaped wavefront like this. And we need a particular direction in which the wave is traveling. No? An S-shaped wavefront, if the wavefront is like this, okay, assume the disturbance is propagating to the right. Draw the shape of this wavefront after some amount of time, after a short while. So how is this S-shaped wavefront formed? How exactly it is formed? It's not necessary, but basically this S-shape as of now is a collection of two semicircles. Okay, and those two semicircles have the same radius at this moment. So after some time, if the disturbance is propagating to the right side, okay, effectively propagating to the right side, try to predict the shape of the wavefront. You just have to imagine every point on this wavefront as a source of waves, draw wavelets around those points, and then draw common tangential surface. Okay, follow these steps, you will get the shape of the wavefront. Do this, all of you. Okay, can any of you describe the shape of this wavefront after a short while? If you consider every point on this wavefront as a source of waves and the disturbance is effectively propagating to the right, what is the new shape of the wavefront? See, the idea is simple. As I said, you have to consider every point on this wavefront as a secondary source of waves. So assume this point is one source and so on. Okay, this will take some time, just a moment. And you imagine them producing wavelets like this, okay, secondary wavelets. At every point you will have to visualize. Okay, I have this copy paste facility, so I can do that. If you're doing it on paper, you'll have to draw circles, and you have to ensure that the radii of these circles are equal. Okay, see, we want to find out the shape of the wavefront after a time delta t. Now, for every wave, there is a particular speed with which it travels through a medium. Okay, in fact, the speed of mechanical waves depends on elasticity and inertial properties of a medium. You must have studied in sound waves Okay, speed of sound in air, speed of waves on a string, they depend on elastic and inertial properties of the medium. So if the medium is same everywhere, the speed will be same everywhere. If speed is same everywhere, the expansion of the disturbance will be same everywhere in a particular amount of time. Okay, so all these circles will have to be of the same radius. And since the disturbance is effectively propagating to the right, now you draw a common tangential surface to all these circles. It goes somewhat like this. So you will get another S-shaped wavefront, but there is a difference between the original wavefront and this one. This new S-shaped wavefront that you see, okay, is not two semicircles of the same radius. One has a smaller radius and the other one has a bigger radius. Okay, so it's still an S-shaped wavefront, but it's a distorted S. Fine. So this way you can predict the shape of a wavefront after some time using Huygens wave theory, okay, or wave principle. So effectively, the disturbance has propagated like this. Is this clear to all of you? Any doubt in this? Okay. So using Huygens principle, we can predict the shape of a wavefront after a certain amount of time. Okay, and there's one more point you can observe from all these visualizations. You consider the circular wavefronts on a water surface itself, okay, on a plain water surface. The wavefronts are in the shape of circles, that's fine. But how exactly are the waves propagating? The waves are propagating away from the point source, radially outwards, like this. Okay. The set of particles which undergo the same phase of disturbance, that set is circular in shape. But how is the energy traveling? Okay. Or how is the momentum traveling? They are traveling in radially outward directions like this. So this is the wave direction. Okay. The direction of propagation of the wave. And you can see that the direction of propagation of the wave is always perpendicular to a wavefront. You can observe that everywhere with every wavefront, not just here, even in this diagram. The energy spreads radially outward from the sound source. Okay, it spreads away from, or the sound travels away from the source of sound. So sound is traveling radially outwards, but how are the wavefronts? Spheres, concentric spheres. So here also, the angle between the wavefront and the exact direction of the wave is 90 degrees everywhere. Okay, this is a very important property to remember. Wavefront is perpendicular to the direction of propagation of the wave. Even here, even if it is cylindrical wavefronts, okay, the energy is traveling away from this linear source. In every direction it is traveling. On the screen, you can say it is traveling to the right and left. And here also you can see that the direction of wave propagation is perpendicular to the wavefronts. So remember, waves always travel perpendicular to wavefront. Now, this idea can be used in reverse also. If you know a wavefront, okay, if you are given the shape of a wavefront, you can tell how the wave is traveling. Like what we have done in this last example. We drew the shape of the wavefront after a short amount of time. Okay. And see, these black arrows that I have shown is how the energy is traveling, is how the wave is actually traveling. Okay. All these black arrows are perpendicular to the wavefronts. Wherever they cut the wavefront, they are perpendicular to it. So this is the direction in which this is the effective way in which the energy is propagating. Okay, effective direction in which energy is propagating at every point. So remember this point also. The direction of propagation of a wave is perpendicular to the wavefronts at every point. Okay. Next, assume there is a point source. Okay. Let's say this is the point source of waves, S. Let's consider on a two-dimensional medium itself. Let's consider the screen itself. Okay. Again, you think of it as a water source. You can imagine circles expanding from this source. Fine. Just a moment. Let me take one circle like that, just to help you in visualization. So we'll only look at one side. Okay, waves propagating to one side. The circles go on expanding. We are assuming an ideal case where there's no loss of energy. Okay, so the wave travels as long as the medium is present, as far as the medium is present. Okay, so basically these are wave fronts. Okay, every circle is a wave front, no, on the surface of water. So these are wave fronts, and we know waves propagate perpendicular to wave fronts. Now you imagine the actual wave propagating from this source. Now they'll be propagating in all directions, that's fine. You take one wave going like this, and another one going like this. These two have a very small angle between them. Okay, this is wave 1 and this is wave 2. They have a small angle between them. And you look at the wave front. It's a circular wavefront on a two-dimensional surface like the water surface. These wavefronts are circles. But you consider the part of the circle which is between these two waves. Now, as the circles expand, this small part of the circle appears almost linear. Okay, it appears like a straight line. It is a curve actually, but it appears like a straight line. Fine. If you take the gap to be very small, you can assume it's a straight line. So basically, what we are saying is, if you go far away from a point source, see this source is a point source. If you go very far from it, in fact, you imagine a wavefront somewhere here. Okay, this wavefront's radius will be very large. And you take two waves, maybe one like this, and another one making a very small angle with it, or very close to it. These two waves have a very, very small angle between them, as you can see. They are almost parallel to each other. Okay, and if waves are almost parallel to each other, the wave front will almost be linear, right? So if there are parallel waves traveling anywhere in space, okay, let's stick to two-dimensional medium only. Suppose there are a set of parallel waves traveling like this. This is one, this one. These are waves. Okay, actual direction in which the waves are propagating. So let's say there's a set of waves traveling like this. Then their wave fronts must be like this. This is one wave front, maybe a crest. In between, there will be a trough and another crest here, trough and another crest here. So these become wavefronts, or these must be the wavefronts for this set of parallel waves. Okay, see these circles, it's not just one circle. No, as the source keeps on creating the disturbance, the circles will keep getting produced. So there are many circles, there are many wavefronts. Like I have indicated two waves in purple here, these two. They have many wavefronts along their way, okay, as they propagate. This is one wavefront, this is one wavefront, this is one wavefront, so on. Okay, so if the waves are parallel, the wavefronts will be straight lines on a two-dimensional surface or a two-dimensional medium. They appear like straight lines. If you visualize this in 3D, can any of you tell me what will be the shape of these wavefronts in 3D? Suppose there is a bundle of waves, okay, traveling to the right, bundle of parallel waves traveling to the right. What will the shape of the wavefront be? If there's a bundle of waves traveling in the same direction, what will the shape of the wavefront be?
Sir, is it cylindrical?
Rishi, why do you think it will be cylindrical?
Sir, because over here it's a linear mass, so
Mass, it's a linear wave. Okay, waves are see in two dimensions, it's a linear collection of, or you can say it's a linear wavefront. So the collection of particles which oscillate in the same phase, if you connect them, you get a straight line. If you imagine this in 3D, how does it look is what I'm asking. I think you are confusing it with this example where the source was linear. Here the source is linear and the disturbances are also linear. That's fine. How do I put this? Just a moment. Okay. Here, actually, if you visualize in 3 dimensions, no, the waves are propagating like this, radially outward. They are not parallel waves in this case. Okay. And for these waves, if you draw a wavefront, that becomes cylindrical. But if the waves themselves are parallel, and you have to imagine a surface which cuts all the waves perpendicularly, how will that surface look is my question. Okay, you all do this. You just imagine a bundle of sticks. Okay, you must have seen, no? If you want, I'll show you an image also. You imagine a bundle of sticks. Can you visualize a surface which cuts all the sticks perpendicularly? Is the question. What will the shape of that surface be? A surface which cuts all these sticks perpendicularly, what will the shape of that surface be? Okay, Nitya, your answer is correct. It will be a plane, a flat surface. You can visualize it like this. Fine. Suppose there is a bundle of parallel waves. And if you imagine a surface cutting all the waves perpendicularly, it looks like this. It will be a flat surface. These are the waves, okay? The parallel beam of waves. And this is the surface which is perpendicular to all the waves. So this becomes the wave front. Okay, in 2 dimensions, it looks like a line. If you extend this in 3D, in Z direction, means perpendicular to your screen, you extend it, the line becomes a plane. So basically what I'm saying is a parallel beam of waves has a planar wavefront. Okay, see, this also gives you a way to imagine a wavefront. Wavefront is basically a surface which cuts the waves perpendicularly. Here, since all the waves are in the same direction, parallel beam of waves, you just imagine a surface which cuts them in the perpendicular direction, then that will be a flat surface. Okay. On a water surface, if you visualize, the waves travel radially outwards. Okay. Just a moment. On a water surface, if this is the source of waves, the waves actually travel radially outward like this. Then in that case, if you imagine a surface cutting all of them perpendicularly, it becomes a circle. In 2 dimensions, it becomes a circle. In 3 dimensions, it becomes a sphere. This is the wavefront. Okay, it is cutting the waves perpendicularly wherever it touches them. Okay, so that way you can draw the wavefront based on the way the waves are propagating. Is this clear to all of you? A parallel beam of waves, why it has a planar wavefront? Okay. A linear source of waves, how it produces cylindrical wavefronts. In 3 dimensions, these will be cylindrical wavefronts. Okay, you imagine waves traveling away from that line. You need a surface which cuts all those lines. Then that surface will, which cuts all those lines perpendicularly. Then the surface will have to be bent like a cylinder, okay, hollow cylinder. Fine. So let's summarize what all we discussed today. Basically, what we learned is about how mechanical waves propagate. Fine. We know that mechanical waves, be it sound waves or water waves, they bend when they pass close to a boundary. Okay. Why waves bend when they pass close to a boundary is what we have discussed now. Every particle of a medium which is disturbs the particles around it. That means every particle behaves as a source of waves, new source of waves. So once a particle is disturbed, that particle is a source of disturbance for the surrounding particles. That's the idea. Now, how that idea is applied to explain the behavior of mechanical waves, especially waves that we see on the surface of water and sound waves, is what we discussed today. And in the process, we talked about something called a wavefront. Wavefront, by definition, is a continuous distribution of points, or you can say a locus of points, which oscillate in the same phase when waves pass through them. Okay, means they should all be going through the same phase of disturbance. So if it's a transverse wave, all the particular points on a wavefront will reach the crest, the topmost point at the same time. They'll all go to the trough at the same time. Okay, that collection of particles is what you call as a wavefront. And then we discussed the different shapes of wavefronts. A point source on a 2-dimensional medium creates circular wavefronts. In 3-dimensional medium, it creates spherical wavefronts. Okay. A long linear source creates cylindrical wavefronts. A point source can create planar wavefronts also very far away from it. Actually, it creates spherical wavefronts. But if you consider a very small part of that sphere, it appears like a plane or a flat surface. In 2D, it's a line. In 3D, it's a plane. Okay, like see, the light we receive from the sun is actually a sphere. Okay, and the wave fronts, if you think of the sun as a source of waves, the wave fronts it creates are spherical. Okay, the light from the sun will be going radially outward, but the sunlight that reaches Earth is almost a beam of parallel light. Why? Because the Earth is so small compared to the size of the sun, and it is so far from the sun that if you draw waves from the sun to the Earth, they will almost be parallel lines. So it's like you consider this S itself as the sun, and Earth is here. Okay, it won't even be this big compared to the sun. Okay, it's very minute, you know that. And the distance is very large. Fine. It takes light 8 minutes to travel from sun to earth. That is how far it is. That distance between sun and earth is called one astronomical unit. Okay, the average distance between sun and earth, it's called one astronomical unit. It's a very large distance. So you imagine light from the sun falling on earth, it will almost be a parallel beam of light. So a point source can create linear wavefronts also, or planar wavefronts also at a very large distance from it. Okay, remember that. And yeah, if it's a planar wavefront, the waves are parallel to each other, and reverse. If the waves are parallel, it's a parallel beam of waves, then the wavefront is a planar wavefront. Okay, thank you all. We'll continue on Thursday morning. So next class, what we are going to discuss, we'll solve a few problems based on Huygens wave principle, and then we will discuss Young's double slit experiment, how it was actually proved. Okay, what are the ideas that were used and how it was actually proved that light has wave nature.